Hello, my name is Nargis and I'm a PhD student at Software Institute of Università della Svizzera Italiana here in Lugano, Switzerland. I'm going to present our work on taxonomy of real faults in deep learning systems. I'm a member of PRECRIME research group which is funded by ERC Advanced Grant Program. These days, deep learning is finding its way into an increasing number of areas in science and industry. Its application ranges from image recognition to more critical tasks such as fraud detection, autonomous driving, or diagnosis of various diseases. We define a DL-based system as a software that contains at least one deep neural network as its component. One example of such system could be an object detection model in an autonomous car. As DL solutions are adopted in a large number of tasks that are safety critical, ensuring their robustness and understanding the reasons behind the failures that occur in such systems becomes crucial. We define failure as the inability of a DL component to exhibit the expected behavior specified by performance requirements. On this example on the right, you can see an autonomous car that fails to follow the track and goes into the lake. Usually, a root cause of a failure is a fault that occurred during the development of an application. The notion of a fault in DL systems is more complex than in traditional software, as the behavior of DL-based system is not explicitly programmed in its source code. It also depends on a number of other aspects such as model architecture or how the systems are trained. As a result of these differences, in order to develop efficient techniques tailored specifically for DL systems, there is a need in thorough analysis and classification of DL-specific faults. This served as a motivation for this work. To construct our initial classification, we started by identifying the most popular frameworks that provide developers with building blocks to construct their models. This happened to be PyTorch, Keras, and TensorFlow. Then, to gather information on faults that occur during development with these frameworks, we refer to two major platforms that are popular among developers, GitHub and Stack Overflow. To extract the initial dataset, we use data exploration tools available for these platforms. Then, by applying a rigorous filtering procedure that enabled us to filter out tutorials, projects, and general how-to questions, we were able to obtain a final list of commits, issues, PRs for GitHub, and posts for Stack Overflow. Then, the data collected from GitHub and Stack Overflow was manually analyzed by all authors following an open coding procedure. Each author independently labeled the documents assigned to him or her by defining a descriptive tag of the fault. Each document was labeled by at least two authors. The labeling process was supported by a web application that we developed specifically to classify the faults and to solve the conflicts. During the labeling, we followed a specific procedure for handling special and corner cases. We first checked if a fault is in a DL component itself. If the fault happened in the framework, we marked such issues as false positive. If the fault has happened in a DL component, we then checked whether this fault is a rather generic programming fault. If yes, these issues were marked as generic. Otherwise, the faults that were DL specific were then checked on the subject if they can be meaningfully labeled. In case there were not enough information, these issues were marked as unclear. Otherwise, the evaluator provided a specific tag. The labeling process was organized into 6 rounds, each of them followed by a meeting among all authors to discuss the process and to solve the conflicts. The conflicts arise when there was no agreement between two evaluators, and the app automatically assigned the issue to an additional evaluator. In case of further disagreement between these three evaluators, the conflicts were discussed and solved during such meetings. On this table, you can see an information for each round, and it features the number of artifacts that were analyzed, the number of artifacts that were identified as related to DL, and the number of unique leaves that contributed to the taxonomy during the labeling of this round. After the 4th round, we have started to build the initial taxonomy in a bottom-up approach, which means that we first group the tags that correspond to similar notions into categories, with some of them later combined in parent categories. We decided to stop the process once a new labeling round did not result in the creation of any new inner categories in the taxonomy. In total, we were able to analyze 1,059 artifacts, 149 of which were related to DL. While Stack Overflow and GitHub are rich sources of information, the nature of these platforms limit the reported issues to mostly code-level ones. To get a more complete picture, we decided to perform interviews with researchers and industrial practitioners involved in DL development. We have recruited and interviewed 20 developers with various backgrounds and levels of expertise, from personal contacts, top answerers on Stack Overflow, and a freelancing platform called Upwork. The participants were interviewed by two of the authors, with one of them being a lead interviewer and another asking additional questions. The interviews were semi-structured, which means that we started with one very general question, and then based on the given answers we proceeded with more specific questions. Almost all of the interviews were done by Skype, and they were all recorded given the consent of the interviewers. They were then transcribed to allow the further analysis of the contents. We analyzed the transcribed interviews through the manual open coding procedure. To do this, each of the documents was assigned one moderator and two evaluators. The role of each evaluator was to perform the open coding task, while the moderator's role was to identify and resolve conflicts between the evaluators. The moderator was always one of the authors that performed the interviews, and the other interviewer was the first evaluator. The second evaluator was assigned from the authors who did not participate in the interviewing process. The open coding was performed manually in the Google Docs online tool. Overall, we were able to tag 297 pieces of text, and 226 of them were relevant to DL. So in total, our taxonomy is based on the manual analysis of 1,356 artifacts, with 375 of them related to DL, and which are instances of 92 unique fault types. Our final taxonomy, which you can see on this slide, consists of 5 main categories, with 3 of them further divided into inner subcategories. Let's now focus on 2 of them that are the most specific to deep learning. The first one is the model faults, which gathers the types of faults that are related to the selection of the model and model architecture. Then examples could be a missing dropout layer or a wrong initialization of the weights of the network. Another category is the training faults, which gathers all the faults related to the training phase. A fault from this category could be a suboptimal learning rate, or wrongly processed training data, or maybe the usage of an unbalanced training dataset. To ensure that the final taxonomy is comprehensive and representative of real DL faults, we have validated it through a survey that involved a new set of practitioners or researchers that were recruited through the same sources as for the interviews. To conduct the survey, we used Qualtrics web tool. We provided our participants with descriptions and examples of the categories or of the larger subcategories, where we asked them whether they encountered such type of faults, how severe it was, and how much effort it required to identify and fix it. As a result, there were no category of faults that wasn't confirmed by our participants, with the average success rate of 66%, which confirms that all of the categories in the taxonomy are relevant. To conclude, as a result of our work, we have obtained a validated taxonomy of real faults in deep learning systems. To our knowledge, this is the first work on DL-specific faults that includes interviews with developers. The possible usage of this taxonomy could be as a reference for researchers. It could also aid developers to avoid the common pitfalls, and it could also serve as a guidance for testers of DL-based systems. In our future work, we plan to use the taxonomy as a guidance to improve DL systems testing and as a source for the definition of novel DL-specific mutation operators. If you're interested, here you can find the link to our replication package and to the websites of our research groups. Thank you for the attention.